of the Newman-Janis algorithm. Please, Philip, go. You can begin.
Okay, yes. Hello. As it was stated, I will be speaking about the physical interpretation of the Newman-Janis algorithm. This presentation is based on two papers that I published with Paolo Gondolo while I was at the University of Utah. So, as the original Newman-Janis algorithm was a procedure which allowed for the derivation of the Kerr-Newman black hole and a rederivation of the Kerr black hole. This procedure was extended by Gurses and Gursey, who showed that a version of the algorithm can create a rotating Kerr-Schild spacetime from a static spherically symmetric Kerr-Schild spacetime. This version specifically has been getting a lot of attention in recent years because it's popular with non-singular black hole research, because many of the non-singular black hole models are Kerr-Schild spacetimes. There was a further extension by Drake and Szekeres, which showed that there is a version of the algorithm which can create rotating spacetimes from arbitrary spherically symmetric spacetimes. The fact that we have this method of generating rotating spacetimes is interesting. However, exactly what is happening physically with the algorithm and the properties of the resultant spacetime are not immediately apparent. So, in the original form of the algorithm, you could write the Schwarzschild or Reissner-Nordström metric in advanced null coordinates as follows. If the Q term goes to 0, then it's just the Schwarzschild metric. If we re-express this metric in terms of a set of vectors L, N, and M, where we allow for the R coordinate to take complex values, and we get the following. Notice that if R goes to its fully real, then this M term goes to 2M over R, and this Q term goes to Q squared over R squared, but these terms appear to have been broken up in terms of R and R bar differently. Also, notice that there is a purely imaginary component in the M vector. However, when the metric is built as shown here, in spite of the complex components in the vectors, the metric remains fully real. The next step of the algorithm is to do a complex coordinate transformation, which basically amounts to some complex rotation with a parameter A, and we get our new set of vectors as shown here, where we introduce a shorthand that we'll be using a lot during this talk. Capital sigma is equal to the new radial coordinate squared plus a squared cosine squared. If we reconstruct the metric as before, featuring these new transformed vectors, we end up with a fully real metric that is the Kerr-Newman metric in these advanced null type coordinates. So we have this mathematical procedure which has mapped the Schwarzschild.
Hello, can I ask a question about the previous slide?
Yes.
So my question is, there are those three vectors, the three null vectors L, N, and M. However, there is also this, in case of when this is a real metric, there's a vector. And when we do, is my understanding correct that we actually change the M bar vector when we do this transformation?
Okay, so
Meaning that we are not able to transform all the four vectors, that we transform
okay, so
the m vector
in-
and then we take m bar of the transformed m vector rather than transforming m bar in.
yes, you take the m bar of the transformed m vector.
Thank you.
Okay. Yes. So, and then another, so in it, we've found this. So we found this.
Excuse me, there
version-
was a remark that the bottom is not visible on the screen. So, so your slides are cutted down, you know. Just...
Okay. In that case, I think we can. Are you able to see everything now?
Well, this slide is okay, but the previous one was cut. Oh, okay, now it's okay.
Okay. Okay, well, we will just continue like this if it was previously cutting something off. Okay, so one of the things that I had pointed out was that the complexification of the M term and the Q term look rather different, and we could wonder if there was a more systematic way of doing this. And we could also wonder, why did this procedure happen to give us two relevant spacetimes at all? So these questions are partly answered by the Gurses-Gursey extension for Kerr-Schild systems. So Kerr-Schild systems have a special symmetry in that they can be written in terms of the Minkowski metric, a scalar function, and a special vector which is null with respect to both the Minkowski metric and the full metric. When written in particular spherically symmetric coordinates, these will, if they're spherically symmetric, they will appear to look much like the Schwarzschild metric, except now, rather than m being a constant, m is a function of r. If we convert this to advanced null coordinates, we get a metric similar looking to before, except m is a function of r rather than being constant plus the q squared term. We rewrite in the same set of vectors, except now we have to change our n vector, and the n is broken up into r and r bar in this way. So if you were to put in the appropriate m function for the Reisner-Nordstrom metric, you would get the result would be as it was in the previous version of the algorithm, with how the terms were expressed in terms of r and r bar. We perform the same coordinate transformation and we get a new form for the vector n, the same forms for the other vectors. If we reconstruct, we get a rotating metric in these new advanced null coordinates. Well, this would be usable. It is more convenient to work with time-like coordinates, so we can convert to Boyer-Lindquist coordinates using this transformation, where we have a new notation. Delta is r squared plus a squared minus 2r m of r, and then we can obtain a metric in Boyer-Lindquist coordinates. This was something of an involved procedure because it involved a complex coordinate transformation and all of this set of vectors in order to go from the spherical case to the rotating case. But going backwards is very simple. If you take this rotating metric and you set A to 0, it goes back to the spherically symmetric metric. A can therefore be thought of as a rotation parameter. And we have a family of spacetimes for different values of A, which are dependent on the function M, which is the same function in the rotating and non-rotating case. So in order to analyze the physical content of these pairs, it's easier to first put the metric into some new forms. We can draw attention to these principal directions, which we'll call 1, 2, 3, and 4. In the non-rotating A goes to 0 case, direction 1 is just the t direction, and direction 4 is just the phi direction. The directions 2 and 3 are the r and theta directions regardless. It's also helpful to write the Kerr-Schild scalar function and the Kerr-Schild null vector. They have simple expressions. In these coordinates, the expression for the Minkowski metric is actually long and complicated, but it can be verified that has the correct signature and has 0 Riemann tensor, regardless of what the M function is. So it is, in fact, Minkowski metric, although the coordinates make it non-obvious. Now that we have the metric out of the way, we can analyze the physical content through the energy momentum tensor. We have a block diagonal form in Boyer-Lindquist coordinates where the r theta block is already diagonalized. The t phi block has off-diagonal terms. If we take rotation to 0, we get that only the diagonal terms remain, and that the TT and RR components are degenerate, and the theta theta and phi phi components are degenerate. If we diagonalize our rotating energy momentum tensor to determine the eigenvalues, we see that it has the same general structure. We have 2 pairs of degenerate eigenvalues, and these eigenvalues, when we set the rotation parameter to 0, go to what we were obtaining as our eigenvalues for the non-rotating case. Another thing to notice is that our non-rotating time-like eigenvalue is minus m prime over 4 pi r squared. This can be interpreted as minus the density. So if we were to rearrange this, we would get that the integral of 4 pi r squared times the density is m. So m is a mass function. I have seen it specifically called the Keplerian mass in the literature. Because we have 2 pairs of 2 degenerate eigenvalues, this is called Segre type 1, 1, 1, 1. In general relativity, we typically use Segre type to examine the structure of the mixed index energy momentum or Ricci tensors. By the Einstein field equations, these have an equivalent Segre type. 1, 1, 1, 1 refers to a pair of degenerate eigenvalues which have space-like eigenvectors, and a second pair of degenerate eigenvalues which are spanned by a space-like and time-like eigenvector. If we have that written in this form, that means that all 4 eigenvalues are degenerate. When we have eigenvalue degeneracy, we have freedom with the eigenvectors. And so it's possible to write our eigenvectors in terms of the directions 1, 2, 3, and 4 from earlier. We have our eigenvector, which is a linear combination of directions 1 and 2, which spans our density and what we call the parallel pressure, and our perpendicular pressure is a linear combination of vectors 3 and 4 as an eigenvector. Physically, these symmetries of the energy momentum tensor can be interpreted as boosts for the 1, 2 directions, and as a rotation for the 3, 4 direction. If we choose a normalized time-like version of our 1, 2 eigenvector, this can be interpreted as a 4 velocity with some boost parameter, which I just write as W here. Although the boost parameter is arbitrary because of the boost symmetry, it's possible to find an angular velocity term using the following method, and because the phi and t components of the core velocity have the same coefficient, the arbitrary boost parameter will cancel out, and we'll be left with this particular expression for the angular velocity as defined in this way. It is interesting that this has no dependence on m, so it's the same for all Gurses-Gursey systems, regardless of what the mass function happens to be. This is also, if you use graph, it's basically half of a Cauchy distribution. So we've analyzed the general structure of the energy momentum tensor, and we determined that it has a specific Segre type. So it automatically satisfies that the density is equal to the minus of the parallel pressure, and the two perpendicular pressures are equal to each other. We could consider some situation where we're writing an equation of state in terms of thermodynamic variables. So we could have some function of pressure, density, temperature, other variables is equal to 0. What we were particularly interested in were systems where we could write some equation of state in terms of the density and the perpendicular pressure. For spherical systems, this is often easy because if either eigenvalue is monotonic in R, it's possible to derive some equation of state F, which is satisfied in the spherical system. This equation of state is usually not preserved when we pass into the rotating system, but we did find that under certain circumstances, the equation of state is preserved. So, in order to determine what the circumstances were, we take partial derivatives of the equation of state. We get that these expressions, the partial derivatives with respect to r and theta, would be equal to 0. For these two equations to hold in non-trivial situations, we get this condition on the partial derivatives of the eigenvalues themselves. If we use the expressions for the eigenvalues, we ultimately get a differential equation for the function m, which ends up being the following. In the spherical case, this is reminiscent of a mass function with a Schwarzschild term m. The k over r term ends up being an electric field Reisner-Nordstrom term. This term with little lambda times r is basically a string cloud term, and this final term is, in spherical symmetry, a de Sitter-like term. And we also have that there is a constraint on the values that the coefficients for these different terms take. Using this mass function, we can get what the eigenvalues are in the rotating case, which if we have the string cloud or de Sitter terms with the lambdas, this gives us a maximum rotation that is compatible with the null energy condition as shown here. So if our rotation parameter A exceeds this value, the null energy condition is violated somewhere. Notice that if we were to set both lambdas equal to 0, we have simply a Reisner-Nordstrom-like mass function. So the Reisner-Nordstrom black hole to the Kerr-Newman black hole is one of the situations where the equation of state F of rho p perp is satisfied. In the case of a electric field energy momentum tensor, the equation of state is actually that the density is equal to the perpendicular pressure. If we keep all of these constants, allow them to be arbitrary, then we can derive that this equation of state here, which for short we just call the Gurses-Gursey equation of state, still applies. So the square of the difference between the density and the perpendicular pressure is equal to 4 times rho times capital lambda over 8 pi. We call this rho lambda because it would be the density of the de Sitter term in the spherically symmetric case. This has a vacuum energy point at rho equals rho lambda, and at extremely high densities, which are far off what we can see on this graph, it does behave in a roughly electromagnetic way in that the density and perpendicular pressure are approximately equal to each other. So in addition to the Reisner-Nordstrom black hole, another fairly simple case we can do for the M function is we set everything to 0 except for capital lambda. This is, as I mentioned, a particular version of de Sitter space in the non-rotating case. This space-time, the Gurses-Gursey rotating version of de Sitter space, has been previously studied, and one of the names that is commonly used for it is rotating de Sitter. In a sense, this name is fine because it is a rotating space-time which is based on the de Sitter metric in the non-rotating case, but in the rotating case, it has inhomogeneous and anisotropic properties. This is easy to see in that especially between these two corresponding points here and here, we see that the perpendicular pressure is different than our eigenvalue in the parallel plane. We also see that the perpendicular pressure is lower than the eigenvalue in the parallel plane. So in fact, the null energy condition is violated here. It's violated in general everywhere except on the equator. Now, we can see that this Gurses-Gursey rotating de Sitter no longer follows the vacuum energy equation of state. However, it does still follow the equation of state given on the previous page. Specifically, that is in this this region of the graph, the different points are somewhere in this region of the graph. Okay, so as a recap of the Gurses-Gursey method of the algorithm, we preserve the Kerr-Schild nature of the metric when we pass into the rotating case. We will in general preserve our 1, 1, 1, 1 Segre type between the rotating and non-rotating cases. Although if we were the fully degenerate with 4 eigenvalues, this is in general not preserved unless we are in the identically vacuum case, which would be Schwarzschild to Kerr. Because there is an eigenvalue degeneracy, there is freedom in the eigenvectors. Regardless of this freedom, we can construct a 4 velocity, which ends up implying a unique angular velocity, which is shared by all m functions. We get that the equation of state is definitely preserved for Schwarzschild to Kerr and for Reisner-Nordstrom to Kerr-Newman. It is preserved in the more general case that we also derived. However, if we want to preserve the pure vacuum energy equation of state or some nonlinear electrodynamics or non-singular black hole, if we had the equation of state for those, that will typically be altered when we pass into rotating version, and we might get violations of the null energy condition. We could examine the Gurses-Gursey equation of state in different contexts as well, such as cosmology. I wrote a paper about anisotropic Bianchi spaces featuring the Gurses-Gursey equation of state earlier this year. So, as I mentioned, Drake and Szekeres came up with a further version of the algorithm for which you could use a arbitrary spherically symmetric spacetime as arbitrary statically spherically symmetric spacetime as the seed system rather than just Kerr-Schild. So one way to write what they did is to use the following functions where h is in terms of the mass function m, f is h, and then there's this scaling function j. The corresponding rotating metric is written here. We are using a new shorthand, sigma j, which is similar to the last sigma shorthand, except now there's j in the r squared, and then we plus a squared cosine squared. As before, it's possible to write this in terms of principal directions. So we have our directions here. This is not in general Kerr-Schild unless k is 1. If k is 1, then we recover the Gurses-Gursey. If j is 1, we recover the Gurses-Gursey metric. And then it would be Kerr-Schild, and we could rewrite in the Kerr-Schild form, but in general, it's arbitrary. So we don't have a Kerr-Schild metric or scalar function that we can write. The actual expressions for the energy momentum components are too long to fit on a single slide. If you really want to see them, I have them in the backup spread over a few slides, but we can use a tetrad to define a local Lorentz frame, move into local Lorentz frame, and analyze the structure of the energy momentum tensor. So using this tetrad, we see that our energy momentum tensor in this particular local Lorentz frame has a block diagonal structure again. This time, the r theta block is not in general diagonal. There can be an off diagonal term in the r theta block. and there's an off-diagonal term in the T phi block. We did not choose a tetrad which fully diagonalizes the energy momentum tensor because we determined that there are certain cases where that is not possible to do with a local Lorentz frame. We can see by... Was someone asking a question? Oh,
No.
okay. I thought I heard something, but maybe it was maybe it was nothing. Okay. But we can see using the metric in this local Lorentz frame that if delta is negative, then our second direction is our time-like direction rather than our first direction. In the spherically symmetric case, this corresponds to being behind an event horizon. So that is equivalent to delta switching sign here. But if delta is greater than 0, then our orthonormal metric has the standard form. So with those components of the energy momentum tensor, it's possible to build traces and discriminants of the blocks. Using these traces and discriminants, we can figure out what the eigenvalues are and figure out what the Segre type is. So when we are in front of an event horizon, or we have delta is greater than 0 and t is time-like, we could have a few situations for the T phi block. They could either have distinct eigenvalues, which would be Segre 1, 1. If this discriminant is 0 and there's no off-diagonal term, then it is Segre 1, 1 degenerate. So we have degenerate T phi eigenvalues. If the discriminant is 0 and the off-diagonal term is not 0, in this case we have degenerate eigenvalues but a double null eigenvector. This is called 2 in Segre notation. If the discriminant is less than 0, we have a pair of complex conjugates as our eigenvalues. This is notated as z and z bar. The r theta block is simpler. We will have two space-like eigenvectors, and they will either have degenerate eigenvalues or no degenerate eigenvalues. If delta is less than 0, the character of the blocks are switched. One reason why we couldn't diagonalize with a local Lorentz frame is that in general you can have complex conjugate eigenvalues and these double null eigenvectors. It's not possible to diagonalize such an energy momentum tensor with a time-like local Lorentz frame. It is possible to write out expressions for the eigenvectors in our orthonormal directions in terms of the eigenvalues and the components. These expressions will work most of the time, except for this 1, 1 case, in which case they will go to 0. But in the 1, 1 case, any vector you choose in that plane will be an eigenvector, so it's not, so you could just choose something else. So, as I stated, in general, these Drake-Szekeres systems are very complex. We can't necessarily fit the full components on a slide to look at them, but one system which we found which was possible to do analysis is this system here, where j is a constant and the m function is 0. This is Minkowski space with a scaled time coordinate in the non-rotating case. If we remove rotation or have our standard time scaling, the Riemann tensor for the spinning metric vanishes and it remains Minkowski space. If we have non-zero A or non-1 J, there's typically a non-trivial curvature and an energy momentum tensor associated with this space-time. As an analogy to the rotating de Sitter name, which had been given by others to the rotating version of de Sitter space, which is obtained using the Gurses-Gursey method, we call this spinning Minkowski. So for spinning Minkowski, it is possible to actually write these traces and discriminants of the blocks on a slide. Because m is equal to 0, delta is positive, so it is the 3-0 block or T5 block, which could have the varying Segre type. All of these components have a power of A and at least one power of J minus 1 in the front. So if A goes to 0 or J goes to 1, all of these will go to 0 because we're back to a flat vacuum space-time. These terms out front also don't change sign as we move throughout space-time. So the sign of the discriminant term here, the D30, which will determine our Segre type of the T5 block, is based on this polynomial in R and cosine theta, which we borrowed the shorthand from Drake and Szekeres. They used the shorthand chi is equal to cosine theta in order to shorten some of these expressions. So we can look at what the Segre type of the various blocks is for this spinning Minkowski space-time. We get that there is, in regions where this D30 is negative, and we have the ZZ bar complex conjugate Segre type that's in gray. We have regions where D30 is positive, and we have all real eigenvalues and real eigenvectors that are 3 space-like and 1 time-like. This is white. On the border between these two, our D30 is 0. In that case, we'll typically have the double null eigenvector that is in black. In addition to the block Segre type, we could have a degeneracy between the blocks. So we could have, for instance, an eigenvalue from the T5 block to be equal to an eigenvalue from the R theta block. Points where this occurs are they are this blue line. There's some degeneracy. So we can, and points where there's like an additional set of degeneracy. So we could, for instance, have 3 degenerate eigenvalues like we do here at this blue point. So we have this, or at this red point, we have 3 degenerate eigenvalues. Notice that at this red point, since it's the 3 space-like eigenvalues which are degenerate, at this point only, we have what is looking like a perfect fluid behavior. Although throughout the rest of the space-time, the Segre type is obviously not perfect fluid because we have these complex conjugate eigenvalues or double null eigenvectors. So one thing that's interesting is that at least cosine is 1 or negative 1, we always have some sort of degeneracy between the blocks, which we can look at in the next figure. So our density eigenvalue is actually lambda T phi minus sorry, yes, lambda t phi minus is our density-like eigenvalue. So when r theta plus is equal to t phi minus, that's in dark orange, r theta minus equal to t phi minus, that's in light orange. So these are a 1, degeneracy. We also have, in general, the other points that could be lambda t phi plus is r theta plus, or lambda t phi minus is r theta minus. These are the dark blue and the light blue fields, and we're showing the cosine is equal to 1 and r for various r over a and various values of the constant j here. There are some Segre types which do not appear in this spinning Minkowski example. So Segre types 3, 1 and 3, 1 degenerate would have a triple null eigenvector. This cannot occur for any Drake-Szekeres system because it's incompatible with the block structure. In theory, we could have had, at least according to the block structure of the energy momentum tensor, a double null eigenvector with degenerate space eigenvalues, or double null eigenvector with all 4 eigenvalues degenerate. This one is coherent electromagnetic radiation, for example. We could, at least according to the block analysis, have had this occur. We did not see it appear when we were analyzing our spinny Minkowski spacetime. So, as a recap of the Drake-Szekeres method, they can have wildly variable behavior. We could get, for instance, even from vacuum space as our seed system, we can get a rotating space-time which features complex conjugate eigenvalues. So the sorts of matter and fields described by the rotating space-time is unclear. Drake and Szekeres proved that the only rotating metric in their version of the Newman-Janis algorithm, which is perfectly fluid everywhere, is the pure vacuum Kerr solution. We find another proof of this in addition to the one they found, but we find that the perfect fluid can occur at isolated spacetime points. And it's worth mentioning that, well, this is more general than the Gurses-Gursey version of the Newman-Janis algorithm. The complexity makes it less used. So, in conclusion, the Newman-Janis algorithm allows for creation of rotating spacetimes from non-rotating spacetimes through a mathematical procedure. However, the rotating version of the spacetime may not correspond to something that can be easily interpreted as a physically rotating version of the spherical system. We will very often have distortion of the equation of state. In the general Drake-Szekeres case, we could have complex eigenvalues to the energy momentum tensor. So if you're using the Newman-Janis algorithm to create some rotating system, you need to analyze the energy momentum tensors of the spherical and rotating systems to determine what sort of correspondence between the two systems can be drawn. it's possible in the future that there could be further developments in this. There has been work on a slightly modified form of the algorithm, which is similar to the Drake-Szekeres, although they use a slightly different notation and a slightly different procedure to go between the rotating and non-rotating cases. This different notation may lead to more usable expressions for the different terms, which could allow for more detailed analysis. Alternatively, people have been using the algorithm, especially the Gurses-Gursey version, on example spacetimes more frequently. Further analysis of these example spacetimes might increase the intuitive understanding of how the Gurses-Gursey systems behave in general. Well, thank you, and are there any questions?
Thank you very much, Philip.
Hello, am I audible?
We have time for questions.
Yes.
Yes, thanks, Philip. I would like to ask you a question. So let us begin with Schwarzschild de Sitter spacetime. Okay. Now, if you apply this Drake-Szekeres algorithm that you mentioned, do you end up with Kerr de Sitter spacetime?
Okay, so typically if the Schwarzschild de Sitter spacetime, if you apply is actually Kerr-Schild, so you can use the Gurses-Gursey version. If you do this, you will not end up with the Schwarzschild de Sitter spacetime, because you will end up with the vacuum energy term won't end up being preserved. You'll end up with a anisotropic stress in the rotating case. So, for instance, there's, I believe in our paper, we found it was called, we mentioned this. So there's something called the Carter black hole.
Okay.
The Carter black hole is a rotating, I believe it's a Kerr-like black hole, but it's on a de Sitter background. You can't reach the Carter black hole using the Newman-Janis algorithm.
You can, you mean?
No, that is not possible.
And
It's
what
not.
about the Drake-Szekeres algorithm? That is a more generalized version, if I understood it correctly.
Yes, it is so you can use the Drake-Szekeres algorithm on more general spherical spacetimes. You don't have to restrict yourself to Kerr-Schild. However, as I had briefly mentioned, Drake-Szekeres had found in their original paper, and we had found an alternative proof of this, that the only globally perfect fluid Drake-Szekeres spacetime is the pure vacuum Kerr solution. So once again, you can't get to a rotating black hole with a cosmological constant using the Drake-Szekeres form of the algorithm either, because that would also be perfect fluid.
Okay. Thanks for answering this. Is it fine if I ask more questions? Do we have enough time for it?
Sure, yes.
Yes.
Okay, so we appreciate a particular algorithm if the rotating space-time that we obtain is the solution of the same Einstein's equation as that of the static input. Now, for example, in case of Janus-Newman algorithm, if you begin with Schwarzschild spacetime, you end up with Kerr spacetime. Now, both Schwarzschild spacetime and Kerr spacetime are the solution of the Einstein's vacuum equation. Similarly, if you begin with the Reisner-Nordstrom spacetime, you end up with Kerr-Newman spacetime. Both these spacetimes are the solution of the same Einstein's Maxwell equation. Now, apart from these two examples, do we have any other examples which have this property? The input static spacetime and the output stationary spacetime, both solutions of the same Einstein's equation. Do we have such examples apart from Schwarzschild and Kerr? Schwarzschild and Reisner-Nordstrom, I mean.
So in a sense, yes. So if I were to, so in a sense, if I have this this m function here, and I make a statement that my equation, I made any statement that my equation of state followed by the matter was this one on this slide here, then this equation of state is preserved when we pass between the non-rotating and rotating system.
Okay. So the output rotating spacetime will be a solution of the same Einstein's equation as that of the input static spacetime, provided this green colored box holds true.
Yes.
Okay. Okay. Thanks a lot. Do
Yes.
we have some known examples in the literature like Kerr-Newman and Kerr? Just like them, do we have some other examples?
I mean not really. We discovered this equation of state in 2019. I don't know if it has, I mean, you could have this, you could imagine a spherically symmetric system with this particular m function, which is due to some substance obeying this equation of state, which you could then set into rotation, and you would get a rotating system still obeying this equation of state. But I'm not aware of any popular examples of this other than the Kerr and Kerr-Newman.
Okay. Thanks a lot. Is it fine if I just ask one small question?
Excuse me, may I ask a question?
Okay.
Because
Yeah,
okay.
Sure.
I missed the one thing. What is this spinning Minkowski? Can you say a few words about it? This is what is it?
Okay. So if I used this as my spherical, if I use this as my spherical seed for the Drake-Szekeres system, this is Minkowski space, but J is a constant here, so I have Minkowski space with a unusual time scaling. If I feed this into the Drake-Szekeres algorithm, we get a rotating space-time that we just called spinning Minkowski for short. It is not, that's just a placeholder name.
Okay, but I would like to ask about this. Is it a solution to Einstein equation with some right-hand side? Is it vacuum? Is it asymptotically flat, etc.? So what kind of solution you get?
It is not vacuum.
Yes.
The matter content is actually rather unusual because there are some regions where we have complex conjugate eigenvalues. So it's not clear what exactly the right-hand side of the Einstein equation would correspond to. I do think that it was asymptotically flat, however.
Because
But
if it is asymptotically flat, it would be nice to know what is the mass. Is it 0 or not? In the asymptotic region, you know, just Minkowski has 0 mass, yeah, IDM mass.
in the asymptotic,
Mm.
well, there
Because
are
I want to mention that there are some well-known Papapetrou class solutions which are somehow singular inside, but outside they are perfectly regular, mass 0, but they have angular momentum. So rotating mass 0 vacuum with singularity inside. And this is pure spin Papapetrou solution, you know?
okay.
And it would be nice to compare those class of solutions with this spinning Minkowski. This is my remark.
Okay, that might be interesting. I do think that it was asymptotically flat, but I don't remember for certain.
Okay, thanks.
Actually, yes. Let me, at least looking at these here, I do think it would be asymptotically flat because we have the highest power of r here is r to the 8th, and in this denominator here we would end up with something like r to the 14th. So it would and then this one r to the 8th, r to the 4th, r to the 8th, r to the 16th, r to the 4th, r to the 8th. Okay, so at least in the Ricci sector, I think it's I think these all go to 0. I don't know. I don't recall looking at the Weil. I don't recall looking at the Weil sector, so it's possible that it's not asymptotically flat in the Weil sector, but it should be in the Ricci sector.
Okay.
Next questions, please. Comments, remarks? I can't hear any. So let us.
But there was one more question.
Okay.
Yes, no, it's guest who asked. Wait, 2 questions and he
Yes.
to ask the question. The person who asked the first 2 questions also wanted to ask.
Yeah, the Kari
Okay, oh.
has the third question. Yes, yes.
Okay,
Yes.
so thanks a lot. I just wanted to clarify one doubt. So suppose you have 2 spacetimes. Both these spacetimes have same Segre type. Now, does this mean that these 2 spacetime are the solutions of the same Einstein's equation?
No, Segre type is more general than that. So for instance, our old so for instance, Segre type, I'll just let's see if I can type something here. Okay, so this is the Segre type, which says we have 3 eigenvectors of space-like character with degenerate eigenvalues and 1 time-like eigenvector with a distinct eigenvalue. This is a perfect fluid. We have isotropic pressure and a density.
Okay.
However, it doesn't tell us what perfect fluid this is. It only tells us that it's a perfect fluid. So it could be water, it could be perhaps
Yeah.
neutron star material, it could be plasma, it could be any any number of things that have isotropic pressure would
Okay.
have this Segre type.
Okay. So for example, just a random example, you begin with perfect fluid dust, you could end up with perfect fluid stiff fluid. These both have the same Segre type because both
Yes.
are perfect fluid.
Yes.
Okay, fine. Thanks a lot. Thank you.
Okay. Thank you, Karim, for your questions.
Thank
Any
you,
other
Professor.
questions? If not, let us thank the speaker again.